Mr. Dito for organizing this school and conference, and I'm very honored to open the session. So, it's always very difficult to give talks when you don't know the audience. So, I will assume that people are familiar with, let's say, basic Sheaf theory. I mean the 6 operations. I speak in the language of derived categories. But after that, I will explain everything. So if you don't know this language and you just hear the music at the end of the talks, maybe you will understand. And of course, you can ask me, don't ask me what is a sheaf, because I assume some basic knowledge. But you can, nevertheless, you can ask a question. But I know we are in Japan and people are shy. So maybe some history. Things began in the 60s. So the main name is Mikio Sato. He founded the Kyoto School on what he called algebraic analysis, which means to treat problem of analysis with tools of algebra, of algebraic geometry, that is sheaves, derived categories, things like that. So he introduced hyperfunction theory in 1960. So that was the starting point of algebraic analysis. And he made a second fundamental discovery in 70s. So this is algebraic analysis and macrolocal analysis. He introduced the sheaf of macro functions, on which now, but the important point is that he explained that it was things which were known but not so clearly since 1 century, that when you work on a manifold, many phenomena are the projection of the manifold from things which are living on the cotangent bundle. So to do macrolocal analysis means you have a manifold and you have the cotangent bundle, and it doesn't mean that you look at sheaves or the distribution or things on the cotangent bundle, not at all. You look at things on M, but from the point of view of the cotangent bundle. And at the same time, also in the 70s, appears the D-module theory with Kashiwara and Bernstein independently. Kashiwara was a student of Sato and Bernstein of Gelfand. And as everyone knows how important D-module theory is, it's a basic tool for a lot of subjects in mathematics, not only analysis, algebraic geometry, group representation, etc. And I think something important appeared in the 80s is with Kashiwara and myself, who introduced the macrolocal sheaf theory. So it's a prolongation of Sato's idea, but but now we work with any sheaf. In some sense, Sato looked at the macrolocalization of the sheaf of holomorphic functions, and we work for any sheaf. And with this theory, we made a lot of results of PDE extremely much easier. And after that, so it's not exact, it's starting in 82. And more recently, in Tamarkin, applied show that macrolocal sheaf theory can be applied to symplectic geometry. Okay, symplectic topology. And he proves, he gave a proof of the non-displaceability, Arnold conjecture, a lot of things. Okay, so I will not, in this talk, of course, I will not do all everything. Huh? It's not, in 3 courses, it's not the subject is not all mathematics or all algebraic analysis. So I will concentrate. So my plan is not the logical one, it's more pedagogical one. I mean that today I will explain basic things that maybe many people know already, and real and complex approach. And thereafter I will be more macrolocal and show the relation and the difference between the real point of view and the complex point of view. In fact, the complex point of view is much easier because there are rings of okay, we'll see. Okay, so today my talk today, I think, will be in 2 parts. So in the first part, I explain the basic macrolocal Sheaf theory and also basic D-module theory. So there are 2 parts. Huh? One is a basic macrolocal Sheaf theory and basic maybe it's too ambitious, I don't know, we'll see. Okay, so as I said, I use the language of sheaves, and I directly define the macro support of sheaves. So this is all details are done in my book with Kashiwara, which is called Sheaves and Manifolds in 90. On the module theory, there is a book by Kashiwara, a small book with a lot of results. You can also look at my webpage. There are a lot of courses on this subject. Okay. So the starting point is a singular support or macro support of sheaves. So first, so you have a real manifold. And you fix a base ring K, a commutative unital ring of finite global dimension. It's a detail. So if you don't like, you choose a field or Z or what you want. Z, R, what you want. And we work with sheaves. So dB Km is a derived bounded derived category of sheaves of K modules. Okay. So I hope that's my basic assumption is that people are not afraid by this. Okay. Maybe the assumption is wrong, but then okay. Okay. So the basic sheaf is its Km, which is a sheaf of locally constant function with value in K. Or more generally, if Z is locally closed in M, I denote by Kz, maybe closed. Okay, let's say closed. The sheaf, the same sheaf on Z but extended by 0 on M minus Z. Okay. So I will not explain here the interest of working with sheaves and not with sets. Okay, because with sheaves you have the cohomology of the sheaf, and when you do operation, there are a lot of informations which are lost with set and not with sheaves. Okay, and maybe some notation. So we have the 6 operation derived, and if you have a morphism, you have the adjoint functor f minus 1 okay, so 5 are classical. This one is more, it's Poincaré duality. And important sheaf also, there is the orientation sheaf. On the dualizing complex, which is isomorphic to the orientation shift shifted by the dimension. Okay, so that's the basic tools that I used. Okay. So I hope you are not too much afraid, but even if you are afraid, don't be discouraged. I will. There are things that you can understand even if you don't know the precise definition of all these things. Okay. So to work in the Dirac category of sheaves means essentially that we work with complexes of sheaves, not one sheaf, but complexes. For example, maybe I give an example. Take as K the complex number, and assume M is a smooth manifold. Then you have the RAM complex. So I write it like that. C infinity 0, M, the differential, until C infinity N, M, 0. So this complex is exact, except in degree 0, where you find the constant sheaf, Cn. So we can look at these two complexes. And in the Dirac category, we don't make any difference between these two things, because this is what is called a quasi-isomorphism. Okay, so that's my explanation of Dirac category, nothing more. We don't make the difference between two complexes of sheaves which are quasi-isomorphic, which means they have the same cohomology. So for me, the Durham complex, or this, the constant sheaf, is isomorphic. They are isomorphic. Okay, so the main definition is that of the microsupport. So maybe I explain the idea. When you have a sheaf or anything, you know what means the support. What means to be 0 in a neighborhood. So you have a sheaf, let's say. So it has a support, which is a closed subset, and it is a complementary of points where in a neighborhood of which you are 0. Okay, but to be 0, you can we can look at in which direction we are 0, in which direction we propagate. So the macro support, singular support of F will be contained in the conormal bundle, in the cotangent bundle. It will be a closed conic subset which describe the direction or the co-direction of non-propagation. So I will be more precise and give a precise definition. So the idea comes from PDE. Many ideas, in fact, even in algebraic geometry, I know people, me included, don't like so much PDE, but one has to say that important ideas from mathematics come from PDE. For example, perverse sheaves comes from the study of partial differential equations. So what is the definition of the macro support? So it will be a closed set. So I will describe the complementary. So let's take an open set W in T star M. So we will say that W does not intersect the macro support if for any function phi from M to R, so not T star M, M from which is let's say infinite of class infinity. For such function and for any x0 in M, such that x0 d phi of x0. So this is some point of the cotangent bundle. So belongs to W. Then you have propagation in the codirection, in this codirection. What does it mean that we have propagation? It means that there is no cohomology supported by phi bigger than phi of x0 f at x0. So it's very difficult to understand, but I will give examples which are very clear. Or if you prefer, this, maybe you prefer this, this is equivalent to say that for any j, the limit inductive limit for hg for v contain x0. So let's define u equals the set of phi of x smaller than phi of x0. Hg of u union v f is isomorphic to hj u f. So maybe I make a picture. So here you have u, which is the set of x, so that phi of x is smaller than phi of x0, x0, d phi of x0, and it means that if you have a section here, then it extends through the boundary. You have propagation in this direction. Okay. So this definition is not so intuitive, I know, but I will give examples on properties. So as I said, the real situation is more difficult than the complex one. After that, I will speak of D modules, which are easier to understand. So the property, the macro support, singular support is closed, as I said, and R plus conic. So R plus acts on the bundle T star M by homothéty in the fiber. Okay. The intersection of the macro support with the zero section. So I denote like Sato, the Sato school. So T star M, M is a zero section of T star M. some people denote it like OM, but I don't like this so much. So recover the support. If you have a distinguished triangle in the DR category, so for those who are not accustomed with the DR category, it's like an exact sequence if you want, then the macro support of Fi is contained in the macro support of Fj union macro support of Fk for I different from J. Okay. Okay. So you have this triangular inequality. And then I will explain now that the main property, the macro support, is involutive. So it's purely geometric, and I will explain. So involutive is the same as co-isotropic. In the US, people use the word co-isotropic. So I will explain this purely geometrical notion in a moment. Okay? Maybe before that, I give examples. So as usual with the definition, you can forget the definition, but remember a few examples on some property. Okay? So don't forget the definition, and let's look at examples. Okay? So example, if F is a local system, or its equivalent in fact, if and only if the macro support is contained in the zero section. If a local system means you propagate in all directions, okay? So there is no macro support outside of the zero section, okay? Another example, local system means locally constant sheaf. No, but no, because I put content. Okay, so if you want F different from 0, M connected, then SSF equal. Okay, satisfying. Okay, another example on which will show you why this notion is important. Take the constant sheaf, take N, a closed submanifold. Then the macro support of the constant sheaf is the co-normal bundle. So immediately, and there are people who have done that, you can generalize. When you have such a result, then you can take the term on the right and put it as a definition of the term, or the term of the left as a definition of what is on the right. So if S is closed, but no more a submanifold, if you want, you are not obliged, you can define the conormal bundle to S in M by definition as being the macro support of the constant sheaf on S. And then you can look, because the conormal bundle is something very important. So now I have a definition of the conormal bundle for any closed subset. Okay, I don't say it's a good definition, but in some time it can be useful. Okay, for example, in the complex case, I'm not sure it's a good definition, but anyway, it's a possible definition. Okay, on maybe I give some. Maybe I give a other example in dimension 1. So M equal R. Okay. And take, so T star M. So this is T star M. Okay, this is M. And take the constant sheaf and the interval 0, 1, closed interval. Okay? So, the macro support, so you see inside the interval, it is locally constant, so it is a zero section. And at the extremity, it's one direction here, positive and negative here. But if you take the constant sheaf and the open, locally closed, I have not defined the constant sheaf on a locally closed set, but you know, I hope, then you find this, the macro support. Okay, so it means it's this. And here. So you see the macro support makes the difference between open and closed, because it's in the sphere bundle. Some other examples. Take M equal V, a real finite dimensional vector space, and let gamma be a closed convex cone, proper or not, I don't know, proper cone. Proper means it does not contain any line. Okay? And if you take the constant sheaf and gamma above 0, then you find the polar cone. Okay, so you have your cone here. And so this is V, and now this is V star, so you have the so you see the smallest gamma is, the biggest the polar cone is. It's a kind of insert Heisenberg principle for sheaves. And in fact, this is a particular case of the involutivity theorem. But before last example, so, which will be developed in the second part of the talk, if I have time. So take X, a complex manifold, M, a coherent D-module, then and take F, the complex of holomorphic solution, what we call SOL of M. Then the macro support of F, singular support of F, is exactly the characteristic variety. How do I denote? Of M. So I will explain this later. Okay. So maybe just before, what means an explicit example? Take a differential operator P, M equal dx over dxp. What is R ohm over dm ox? It is nothing but the complex F, the complex Ox P Ox 0. Okay. So P acting on Ox, this is this complex. So it's an object of the derived category of sheaves. It's a complex of sheaves. And the macro support of this of F is a characteristic variety. And the characteristic variety of M is a set of Z zeta in the cotangent bundle, such that the principal symbol of P Z zeta equals 0. Okay. So I made a link, and I will come back on this link between sheaves and D module. So I want to say a few words on, of course I erased, on what means to be, so the main property, what makes things interesting, is that the theorem that I recall that the SSF is involutive. So what does it mean? Because it has no meaning, say like that. Okay? Because for those who know some symplectic geometry, you know what means a submanifold is involutive, but for a set. Okay? So I will explain what it means because it's important. Okay? So maybe, so it's a parenthesis, there is no sheaf, so you can brace. It's purely geometrical. So to define what means involutive, I need the notion of Whitney cone. Maybe, so you have S contained in a manifold M, and you have, so maybe I don't know how to call it, X, a manifold. And you have X in X. What is the Whitney cone of S? So it will be a cone in the tangent space to X, and it's something very intuitive. Is the limit V is in the Whitney cone if and only if in a local cart there exists xn which goes back to, let's say, x0, okay, which goes to x0 on lambda n positive, such that lambda n xn minus x0 goes to V. So for example, if you have something like that, this is S, then the Whitney cone is the cone which is tangent. My picture is not very good. Which is tangent to S. The set of limit, you have xn, which goes to x0 on the difference. Maybe there is a sign which is not the good one, up to the sign. Okay. And you can also define the Whitney cone for two subsets. So you take the limit, so V belongs to this Whitney cone. If there exists xn which goes to x0, maybe I forget to say xn in S. So you have xn in S, yn in S1, yn which goes also to x0 in S2, on lambda n positive, such that lambda n xn minus yn goes to V. So that's the Whitney cone for two subsets. Okay? Maybe the definition is up to sign. I don't remember. It's written. So now I can define what is to be involutive. So it means, so a subset, now we take a subset S in T star M. Okay. So on some point, so what means on some point P in T star M, So what means to be involutive at P? So the tangent space to T star M is isomorphic to the cotangent space to T star M. This is a Hamiltonian isomorphism, because T star M is a symplectic manifold. So the tangent is isomorphic to the cotangent. Okay? Then the definition, S is involutive at P, means that if you take the normal cone SS and you take the orthogonal, so the orthogonal will be contained in the cotangent bundle to the cotangent bundle, to T star M. But by this isomorphism, it will be, I can look at it in the tangent bundle. And I assume that this is contained in Cp of S. Okay, so that's the definition of being involutive at P. So I give you an exercise. M is R. So take, so now I make picture, okay? We are in T star N. So this is A, and this is B, okay? So prove that A is not involutive, and B is involutive. I think it's if you have understood the definition of the Whitney cone, you can do the exercise. Okay? And it's a good thing that B is involutive because this is the macro support of the constant sheaf and zero infinite. Okay? And this is not a macro support. There is no sheaf with macro support like that. Okay.
So when S is a submanifold, this is exactly the definition.
Yeah, of course. Because in this case, both are equal to the tangent space. And the definition for a submanifold is that the orthogonal to the submanifold is contained in TPS. So the classical definition of being involutive. Okay, so I think in what I've done, I've been fast, of course, but otherwise it took a lot of time. I think the most difficult was the definition of the macro support, so forget it and just look at the operations. So what makes the definition interesting is this property of being involutive, and that's the reason why there are links between sheaf theory and symplectic topology. So now I will briefly explain how the macro support behave with respect to the operation. So you have a morphism. So now I will go, the difficult part is back, so I will relax. So you have a morphism of manifold. So if you take the tangent space, it gives you this diagram. You can decompose the tangent map into morphism like that over M. So this is a base change, and this is a morphism of a vector bundle. Okay. So if I go to the cotangent space, then we find the fundamental diagram, because, so maybe, let's call this F prime and F tau. I denote by tau the projection. So if I take the cotangent, then the first map is a linear map. When you take the dual map, it goes backward. But the base change remains a base change. So we find this fundamental diagram which appears in Sato, Kawai, Kashiwara in the 70s, which means that if you have a morphism of manifold, you don't have a morphism of cotangent bundle. You have a relation, a Lagrangian relation. We can, this bundle, okay. If you prefer, you have T star m, m cross n, T star n, T star n. Here you have T star m cross n. Here you have the conormal to the graph. And this is isomorphic, and you have the projection. Okay, so it's a Lagrange. So this m cross over n T star n is isomorphic to the conormal bundle to the graph. So it's a Lagrangian relation. Okay, so it's well known that when you work with symplectic manifolds, like here, you don't have morphism, but you have symplectic Lagrangian correspondence. So it is a correspondence here between T star m and T star n. So it's natural to ask the question, if I have a first, if I have a sheaf on M, and I take the direct image, what is the macro support of the direct image of F? Assume that I know the macro support of F. Okay. So one candidate. So the theorem, but of course the answer is not for any. There is an hypothesis. Assume F is proper on the macro support of F, then excuse me, is proper on the support of F, which is equivalent, in fact, to saying that F pi is proper on F d minus 1 of SSF, then we have this inclusion. Okay. And for inverse image, there is something similar. When we are in the cotangent bundle, inverse image and direct image are very similar. Right? Assume that you have a sheaf now on N, and assume that Fd is proper on F pi minus 1 of SSG, then the macro support of F minus 1 of G is isomorphic to Fd is equal, is contained in Fd, F pi minus 1 SSG. Okay, so for those who know the, for example, for those who know D-module theory, is very similar to the behavior of the characteristic variety of D-module. And for those who know the wavefront set of distribution, this is also very similar to the behavior of the wavefront set of distribution by integration or inverse image. Okay? So under this hypothesis, the macro support behaves. So maybe I will, maybe I give an example. Take the projection R2 to R. So this is M, this is N, this is F. Okay? And take take this sheaf. Take S and take F, the constant sheaf, and the closed set, which is here. And I take the direct image. So what will I find? I will find something which is constant here between, let's say, 0 and 1. Okay? But with a singularity at 0 and at 1. And what says the theorem? It says that the macro support is contained. Here you can have macro support because here you have a horizontal. All this is horizontal. Okay, but here this is horizontal, but it does not appear. So it's an inclusion. Where is it written? Yeah. We have this inequality, which is not inequality, which is an inequality but not an equality, because this direction does not appear in the macro support of the projection. Okay?
The way that you stated the theorem is,
Yeah.
assume F is proper.
Yeah. So let's say this. Take this set. Okay. Excuse me. Okay. So this is compact. So F is proper. Okay. The support is compact. So F is proper on the support.
No, but what, I mean, it's not clear the way it's stated what the theorem is saying. Assume F is proper on
Support of F.
if and only if.
Ah, yeah, no, not on F. Ah, yeah, this is equivalent. Yeah, this is true. But I don't explain why. But it's an exercise. Okay. Because it's conic. Okay. I don't explain why.
No, it's just a question of formulation.
Yeah, this is true. It's not a mistake. It's true. I wrote it because for inverse image, the first hypothesis has no meaning, and the second hypothesis is very similar. For the inverse image, you assume that FD is proper on the inverse image of this. Okay, so it's symmetric. Okay.
No, it was more basic question than that.
Yeah.
It's just the why if and only between what and what.
It's an exercise. F is proper.
What do you assume? Assume what? Assume F is proper?
Or equivalently, assume F pi. F is proper is on only if.
There's no assume.
Okay. Okay. This is an exercise. Okay, so maybe I translate. Let's forget inverse image. And I translate this for most. So, as a corollary, we have a Morse theorem for sheaves. So it will be a corollary of this one. You take a function psi from Rm to R, which is C1, or C infinity. It's not important. On F is a sheaf on M, and assume psi is proper on the support of F. So set MT is psi by definition the inverse image of the open set minus infinity T. No, open. The open set. Okay, and assume take A smaller than B and assume that psi has no critical value with respect to f in the interval AB. So it means that assume that the differential of phi of x does not belong to the macro support of f for any as soon as a smaller than x, strictly smaller than b, psi of x. Then the conclusion is that the cohomology of psi b, mb f is isomorphic to the cohomology ma f. So the cohomology of f is the same on the slice. Okay, you see, you have m project. So you have the slice MA, MB, and then the cohomology of f is the same as far as psi has no critical value with respect to f. So if you take for f the constant sheaf, then you recover Morse theory. Okay. So you can take more or less this corollary as a definition of the macro support. It would be possible. Okay, so it shows you the link with the Morse theory, but now it's for any sheaf. It's not only. Okay. So maybe now I go to part 2 directly. So I totally change. So it will be easier, or maybe more well known, maybe. So here everything was real. Now everything will be complex, complex analytic. So maybe it's very ambitious to do in 1 hour and a half all sheaf theory and D-module theory. But because tomorrow I want to develop the macrolocal point of view. So here what we have seen that for an real manifold, we have something in the cotangent bundle which is called the macro support with some behavior. Now for D-module. So X is a complex manifold. So you have the structure sheaf. So it's better to call it X OX because OX comes with X. And there is also DX, which is a sheaf of differential operators, so finite orders. So it's defined as follows. So it's a subsheaf of Om over C of OX, OX. Generated, it's a sheaf of ring generated by OX and the vector fields. Okay, so what does it mean? It means that if in a local cart, you can write a differential operator P as a finite sum okay. So I use the classical notation alpha. So X, assume X is open in Cn. So alpha is alpha 1, alpha n. Alpha is alpha 1 plus alpha n. And y power alpha means y1 power alpha 1, yn power alpha n. Okay? Here y is dx, but it can be anything. It's purely formal. Okay? Okay. So when you have a differential operator, so let's remain in a local card. So I can define the total symbol of P as some alpha smaller than m, a alpha of x, xi power alpha. And I can define it more intrinsically as I take exponential minus x xi p applied to exponential x xi. So let's say open some vector space V. So you see xi belongs to V star. Okay. So it will be useful later, the total symbol. So when I will define macro differential operators. So sigma dot P depends on the local card. But something does not depend, it is the principal symbol. So assume it's a polynomial of degree less or equal to m, then sigma m of P x xi is well defined on T star x, the cotangent bundle. And assume it's a polynomial of degree exactly m. So this is called the principal symbol of P, and m is the order of P. So you see the ring dx, so let's call dx m, the set of differential operators such that the order of P is less or equal to m. So this is a filtration. Okay. And what is so we have a filtration, which let's call this f dx, filtration, canonical filtration on dx, filtration by the order. And when you have a filtered ring, you can take the gradient ring. Gr dx is the direct sum of dmj divided by dx g minus 1. Okay? And, yeah, excuse me, I forgot to say something very important for the, yeah, excuse me, I go back to the total symbol. What is important is the formula. What is the total symbol of the product of two differential operators? I forgot this formula. This is sum for alpha 1 over factorial alpha d alpha psi sigma tot of P d alpha x sigma tot of Q. And this is deduced by its Euler Leibniz formula. Huh? So by this formula, you see that when you take the principal symbol of PQ, so this means principal symbol. This is sigma of P, sigma of Q. So it shows that the graded of dx is commutative. So historically, it's very important because, you know, as I said at the beginning of my talk, D-module theory appeared in the 70s only. So it's very, very late compared to other fields of mathematics. Okay? And it's late because people, when I say people, maybe Grothendieck, I don't know, were frightened by the non-commutativity of the ring D. Okay? D is not commutative, so the tools of algebraic geometry do not apply. You cannot apply the classical tools of algebraic geometry. But since it has a filtration and the graded ring is commutative, it's not so difficult to use the commutativity of the graded ring and to obtain result on D itself, which is not commutative. And that was done by Kashiwara in his thesis. Okay? So finally, D is not commutative, but it is almost commutative, thanks to the fact that the graded ring is commutative. So with this, so in fact, one can be, so let's denote by pi t star x to x, and denote by O t star x, the subsheaf of O t star x, subsheaf of functions which are polynomial in the fiber of pi. Okay. Then we can show easily that graph of dx is isomorphic to pi star O t star x. Okay. In the algebraic case, of course, there is not such a, everything is algebraic and polynomial. Okay, so now so by this, one easily deduce the theorem. So all these things are due to Sato, Kawai, Kashiwara, or Kashiwara himself in the 70s. Dx is right, so it's not commutative, so you have to make the difference between right and left, but it's coherent. So you assume you don't know what means coherent, no problem. What means M a coherent left D modules? So it means that locally there exists P0, a matrix, I don't know, Ij dx, such that M is a co-kernel of dx power maybe n0, n1, n0, okay, so a coherent D-module. So many people say, what means D-module theory? So D-module theory means theory of module over the ring D. Okay, and what is a coherent module? It means locally a system, a finite system of linear equations. So locally, you can write dx, I prefer to write things like that. So P0, which acts on the right, dx power n0, m0. Okay. So this is an exact, so locally there exists an exact sequence like that. That's equivalent to saying that M is coherent. And when you have such a sequence, you can try to go further. Here. You go further, you take care of P0. Okay? But by the property of D, this is finitely generated. So this is the image of some dx and 2. So by induction, you construct a sequence dx and 2, dx and 1, dx and 0, m 0, on by a variant of the Hilbert-CZG theorem, it stops. Locally. Okay. So this is an exact sequence. Exact sequence of left D modules. So you have P0, which acts on the right, P1. Okay. So these differential operators act on the right so that the left D module structure is kept. Okay. And as usual in excuse me, there is a mistake. P0 is here. P1. Okay. So as usual, we erase M in homological algebra, and we say that M is quasi-isomorphic to a bounded complex of 3 D modules. What I'm writing here will work for any Noetherian ring. Huh? You have a finite module over a Noetherian ring, then it's of finite dimension. Okay, so now we can define what I explained, what I used before, what means the complex of solution. So let's give a name to this complex. M with a dot is this complex. Okay. So maybe I can write it here. What we are over the M OX will be isomorphic to dx M dot OX. And so if I apply to M dot, I find that, so this is called sometimes for short sol of M. So sol x M is a complex OX over N0 because is contravariant with respect to the first variable. P0 OX over N1 OX over NM 0. Okay. So I have not defined the characteristic variety. What is the characteristic No, I wrote it CHV of M, but sometimes we car of M. Okay, this is not a good notation. It's my tech notation. I'm sorry. So characteristic variety of M. So I don't give details. So you undo M with a good filtration. So I don't explain, I have no time. So it's possible locally. So I don't explain what it means. Then graph of D of M is a coherent graph of dx module. Okay, so you look at it as a pi star O P star X module, and you take the support. So the support of graph M will be contained in T star X and will be the characteristic variety of M. So I give examples. So if M, as I said before, is defined by one equation with one operator, then the characteristic variety of M is a set of X psi in T star X, such that the principal symbol of P at X psi equals 0. Then the main theorem, due to Sato, Kawai, Kashiwara, is that the characteristic variety of M is, again, involutive. Of course, many people say this theorem is due to Gaber. But Gaber gave a purely algebraic proof 10 years later, after Sato, Kawai, Kashiwara. And before Sato, Kawai, Kashiwara, there was a partial result by Gilman, Sternberg, and Quillen. But it was not the complete result. Okay, and now I state the theorem which make the link between, until now I have given a theory of sheaves on a real manifold, on D module on a complex manifold. So there is a functor which goes from D module to sheaves. Okay, it is I take opposite. This is the functor sol, which is R om. Okay, so we have a link from D module to sheaves by sol, this functor. So theorem, so which is due to Kashiwara and myself, if M is coherent, then the characteristic variety of M is equal to the macro support of the solution. So by the way, it gives a new proof of the fact that the characteristic variety is involutive, because macro support is always involutive, okay, coisotropic, for any sheaf. So in particular, in this case. Okay. So, and I want to say that the proof uses only, or maybe I exaggerate, but mainly the Cauchy-Kovalevsky theorem. Okay, so we, using Cauchy-Kovalevsky, we can translate a lot of problem of PDE, of D module, to problem of sheaf theory, just recalling the macro support. So now maybe I have a few time. I want to speak of Lagrangian submanifold. Because when you are coisotropic, in the linear case at least, what do you say? So if you have a symplectic vector space on a linear subspace. Then it is well known that one says that lambda is involutive if the orthogonal of lambda is contained in lambda. Lambda, so involutive, or sometimes one say co-isotropic. Lambda is isotropic if the orthogonal of lambda contains lambda, and lambda is Lagrangian if lambda orthogonal equal lambda. So it's natural when you know that something is co-isotropic to look at what happens in the extreme case. Okay. But I have not defined isotropic for sheaves. Okay. So I say a few words. So let's take the real case. M real, but now I assume that M is real analytic. And after I will look at the complex case. So we say that F is R constructible if there exists a subanalytic stratification. So M alpha, such that F, let's say, weakly constructible. Is that F restricted, if the cohomology of F restricted to each strata is locally constant. So I have not defined subanalytic. So I think I have no time to do that. But you have to admit that there exists a class of subsets, if I can explain after to some people if they want, which is a very nice class, and which is a real analog of complex analytic, but in the real setting. Okay, so there is a theorem that F is weakly R constructible if and only if the macro support of F is subanalytic and Lagrangian. So I have not time to explain in details what it means. I have explained what means to be co-isotropic, but I have not explained what means isotropic, okay, in the subanalytic case. But okay, and we say that F is R constructible if, by definition, if F is weakly R constructible and Hg F of X. So now I assume that K is a field. On this cohomology group are finite dimensional over K. And similarly, if X is a complex manifold, you can define F being C constructible. So you replace subanalytic by complex analytic. So you replace subanalytic by complex analytic. On F, so here you have the category of constructible sheaves, dB, R, C, K, X. On here you have the category of constructible sheaves. No, excuse me, it was M. And you can define similarly dB, K, C constructible, X, any complex manifold. Okay. So that's for sheaves. And for D modules, so recall that so let's now take M a coherent D module. So we know that the characteristic variety of M is co-isotropic, and also it's a complex analytic space. So definition, M is holonomic if the characteristic variety of M is Lagrangian. So now I use my functor Sol. So here I have dB holonomic dx, the opposite category, on theorem due to Kashiwara. When I take the complex of holomorphic solution, I arrive in the category of constructible sheaves. Okay. So if M is holonomic, then a sol of M is C constructible. So it's a very important theorem. And we can ask about the Riemann-Hilbert problem. Is this functor an equivalence of category? So easily the answer is no, but we can look in a subcategory of regular holonomic D module so that it becomes an equivalence. But so maybe I state the Riemann-Hilbert problem. To define some subcategory of regular holonomic, so that when restrict, so this is the functor Sol, so that on this subcategory it's an equivalence. So the Riemann-Hilbert problem means to find such a subcategory and to prove the equivalence, and it was done by Kashiwara in the 80s, and later, 4 years later, by Mepkut, by another proof. Okay, so I think it's enough for today.
Thank you.